turn off the light back here. Okay. All right. We are recording. Let me go over a couple of things. One is an announcement. I can't remember if I told you all this on Tuesday or not. I think I may have forgotten it. I don't think it'll make any big difference to anyone, but I just want to let you know. Normally on Fridays, I'm on the Birmingham West Campus from 8 to 12, usual office hours. Not tomorrow. The reason not tomorrow is I've been assigned, tasked to go to Opelika as a statewide something or another curriculum development meeting that they're having down there. And the meeting goes from 9 until 2. Well, to get to Opelika, we're going to have to leave by 6, okay? So I will not be on the Birmingham, well, I will be on the Birmingham campus shortly before 6 in the morning. So if you really need to see me, that's when you can see me. Or I'll be back sometime probably around 5. So if you want to hang around till I get back sometime around 5, which I have no idea what time that would be, you can catch me then. But those are the only two very brief times I'm going to be on the Birmingham campus tomorrow. So I will not be there during my office hours. Now, this is the other side of that coin. Normally I'm supposed to work only 4 hours on Friday, 8 to 12, okay. But tomorrow I'll be on school business from 6 until 5, which is 11 hours. So I'm going to see if maybe I can take next Friday off as well. That'll only be 8 hours. I'll be not working to pay for the 11 I did work. Okay. So I don't know. It hasn't been approved yet, but I'm going to see. Because, see, normally I work such long hours, I don't have any time to take care of things that need to be done during working hours, except on Friday afternoon. And since I'm not going to be able to take care of them tomorrow afternoon, I've got a bunch of stuff to take care of next Friday. So I'm going to try to see if I can take the day off. Now, that I had already been planning to do. And then last night happened. I don't need to be taking too much of class time, but just to explain partially why things are so disjointed right now. Last night, it was shortly before 10, I was logging into my email to see if I had heard a response from Gary Tracy yet, because I emailed him whenever it was, day before yesterday, and hadn't heard anything by yesterday, so I was trying to see what I could find out. Before I could get logged in, like I said, shortly before 10, I heard just an enormous crash.
A tree fell on your house.
You're close.
Your car?
No, you're close, but not quite there. Okay?
Neighbors?
Wait. Yeah. You got it. Okay?
At least it wasn't yours.
Okay. And that is indeed, I didn't know that's what happened. I just figured the roads were wet and slick. Someone came down the hill too fast and around the curve and slammed into something. Another car, a tree, or something. So I thought, well, let me shut this down. Well, just postpone it. I'll come back to it, but let me go see what's happened just in case, need to call. So I went out, well, before I could get outside, the dog who had been outside burst through the door and just came rushing in the house. She had heard the sound too. She's a real brave dog. And she was just beside herself. So I went out, put on my jacket, went out to see if I could see anything. I figured it must be sort of close that she was. What it was, we had right next to our driveway, mostly on our property, the driveway is real close to the property line, mostly on our property, an enormous oak tree, white oak tree. And I would stand up to the tree and wrap my arms, get as close as I could possibly do around it. I couldn't get halfway around the tree. that big. Its girth had to have been between 12 and 15 feet, because my arm is, fan is about 12 feet. Huh? It is an old tree. Our house is 90 years old this year, and we've seen pictures in the courthouse. We don't know when they were taken, but it was, I think, shortly after it was built, and it was a big tree then. So it has to be way over 100 years. I'm guessing around 120, 125. My wife is guessing 150. It was an old tree. Healthy tree, though. I mean, had leaves like crazy, acorns like crazy. It had fallen down. There was no wind. There was,
Because the ground is so saturated.
The ground is so saturated, wet, just totally wet. Nothing was holding it in place. And as we think about it, we think the thing was probably, with nothing to hold it, it was slowly leaning.
All the time.
Ever since it's been so wet. And finally it got out of its balance and just fell. Hardly anything went on our property. There were a few little twigs and stuff like that in our driveway. Just very minor, brushed them aside. Where the root ball came up, it knocked some things into our driveway, bricks and things like this from the driveway where it was up there. I just threw those into the hole, about 4 feet or more deep hole right there by our driveway. Enormous hole there. But that was it. We had zero damage except we lost a tree.
You had zero damage anybody else's property.
Okay, right next to us, our neighbors, almost the entire tree is in her yard, covering her yard. And the back left fender quarter of her car, maybe the bumper too, it hit, one of the limbs hit that on its way down. So, but she can't get out of the driveway anyway, the tree is there. Huge tree. A lot of its limbs are the size of most trees. Look out at some of these trees, those are about the size of some of the bigger limbs on the tree. It is a huge tree. And,
You're going to miss that shade.
what's that?
You're going to miss that shade.
Oh, absolutely. Okay. I love that tree anyway. But anyway, we had often said, I hope it outlives us, but it didn't. Okay.
So,
Yeah. Huh?
whose responsibility is that?
That's what I'm getting at now.
Say
We-
you ain't paying.
Huh?
Good. You ain't paying. Good. That was good before I got here. I ain't cleaning.
Okay. Here's the deal on that.
Okay.
What I did, of course, we were all rushed out looking. I was still in my clothes, but everybody else was in their sleepwear, and there they were in the roads and stuff. Wow, because it was 50 degrees outside. It wasn't that bad. Like I said, no wind, no rain. But everything was wet as crazy. And we were just looking, just amazed. It just fell over. Literally just fell over. Okay. So I walked to the end of the driveway and saw that the top of it was all over the westbound lane. Our street that we live on has a boulevard in the middle, so the eastbound lane was fine, but the top of the tree was in the westbound lane, and it was covering big portions of the westbound lane. You couldn't drive through it. So I said, I need to go inside and call police to tell them they need to get someone out here to keep people from getting injured driving into the tree. Because it was pitch black dark, there was a street light at the corner, but outside, the tree was not in the light of that, okay? You came around the corner into pitch black and the tree was there all over the road. So I went in to call the police, went to the phone book, and the only number for Birmingham police that I could find in the phone book was for the jail, the Birmingham City Jail. I looked and looked, and I was in a hurry, so I just called the jail and said, I know this is not the right number, but it's the only number I can find for the police. I need the number for the Southside Precinct. Oh, so, yeah, and they started yelling around, stuff like this. So, oh, okay, and they gave me the number of Southside Precinct. Thank you. Because I knew it wasn't a 911 number, call with no emergency like that. So I called Southside Precinct. They got on, told them the whole story. They said, you need to call the non-emergency number. I said, I didn't know this wasn't the no, this is the emergency number. You need to call the non-emergency number. I said, well, it's blocking a whole lane of the street we live on. Someone could hit the top. Well, that's not an emergency yet until they hit. So you need to call the non-emergency number. So, okay, give me the non-emergency number. So they did. They got on the phone, and I started off. I gave them my name. I gave them the address. I told them what happened. Went through all. They started asking me questions. Well, is anyone in? No. Is any property damage? Well, maybe our neighbor's car has some damage on it. So, and I said, but it's blocking the westbound lane. Oh, I said, and cars can't tell that it's there. Oh, well, what's your name? Which I told them at the very beginning. What's your address? I told them at the very beginning. So I went through all of it again, and they will send someone out. So I went back outside, and right about the time I was going down to the street, because I was going to go out and warn people, here came a car around the bend, flying around down a hill, around the bend, and just plowed into the top of the tree. Well, I mean,
Like
the limbs. Yeah. I couldn't get there in time to get him to stop. But he stopped. He slammed on brakes. I don't know if it damaged his car. It didn't look like it did. He was mad. And I said, look, I was inside calling the police, or I would have been out here to warn you.
Now that there's an emergency.
Yeah. So he said, that's why I backed up, and he pulled on and went. Okay? I stopped the next car. So I moved into the street light so they could see me. Okay? And waited to see. And fortunately, there was very little traffic. But then here would come a car. And I'd start waving my hands like crazy as soon as I saw their headlamps. And generally, they looked like they speeded up. I think they thought I was a panhandler. Okay? And they weren't going to stop for me. So when they started zooming by, I said, there's a tree down, And then they'd start slowing, but they would drive all the way up to make sure there was a tree down. And then they'd back up, and on the way out, thank me for telling me. And so I did that for about 30 to 45 minutes until the police got there. Finally, the police got there. He blocked the traffic on the eastbound lane where there was no tree there, and I waved to him to get him to come over. Finally came over and blocked the right one. And then we had to do all the reporting for him. So we were out there, and most of it, our neighbor, but but we answered all his questions and he said, well, I need to get someone up here to clear this debris so we can have the lane. Because right now it's just his car doing it. So he did, and once everything seemed like it was okay out there, I went in to call my insurance company. And I was looking for the number. My wife came in and she found a number. Yeah.
Why would you call your insurance company?
Just to report that it had happened, because I figured their insurance would be contacting mine. So I called, and I think in the insurance, we have really good insurance. It's a great company, but I think they have the rookies at night, because I called and I got the mechanical menu and stuff like this. Please state what you're looking for. Give you the and so I said homeowners policy. Homeowners policy. Okay, wait a minute. And so finally someone came on, homeowners. I said, okay. Gave them my name, gave them information, and I said, you won't believe this. And I went through exactly what happened. And she listened, and she said, well, wow, that's amazing. But you see, we open new policies for people. We start policies. We don't have it. What you need is claims. I said, oh, okay, can you connect me to claims? Yeah, okay, I'll do that. So she did. After a while, they picked up the phone, and the guy came on. I went through the whole spiel again. I said, do you have any of the stuff on the screen in front? I figured they got it. He said, well, I just have your name and stuff. What's the issue? So I went through it all again. And he said, well, I'm going to have to research this. Could you hold? And he was gone for a long time. Finally, he came back and I said, well, I see that you have homeowners with us too. I said, well, yes, that's what I called, and they sent me to you. He said, well, you see, we're auto claims, not homeowner claims. I thought, why would the homeowner department send me to auto claims? And I asked him that. He said, I don't know. It may be that nobody from homeowners is here tonight, and I'm the only one here. So he said, let me see if I can find someone. I'll try to pass all the information so you won't have to go through it again. And he was gone for a long time, which was good. That meant he found somebody who would tell him all the information. So he came back, and he had the other person on the line too. And so I went through it all. I mean, he had told him a lot, but this guy had lots of questions. I could tell he was entering the data as I would tell him and stuff. And ultimately said, well, we can't do anything until the adjusters get here in the morning, and they'll figure something out. So wait until you hear from them. Now, do you need something removed so you can get out and go to work? I said, no, our driveway is clear. It's our neighbor's driveway who's in it, and whose car has been damaged some. So are we responsible for anything, like to get her to work or anything? He said, no, don't do a thing, don't promise, don't say anything. And basically, he didn't quite use these words. So finally I said, so you're saying it's an act of God. Now, someone in my class this morning said an act of nature, and that's probably what I should have said, act of nature. And he said, yeah, yeah. And one of my students this morning said, a tree from their yard fell into a neighbor's yard, stuff like this. They thought they were going to need to, do their insurance. Said, nope, you're responsible for your yard, they're responsible for their yard.
So it came from their yard?
No, it came from our yard into their yard. But everyone has said, what's in their yard, that's their responsibility. The tree was act of nature. I mean, it fell in. Well, here's the bad news, if that's not bad enough. The neighbor's husband is a lawyer.
It doesn't matter.
I know. Yeah, but we're just saying, but our insurance company talked with your insurance company. They know all the laws and stuff like this.
Your insurance company's not going to talk to them. We just went through that. My friend, and just went through that same situation. And the tree from their neighbor's yard fell into his house and all that. Just tore up the things. The tree was huge, like you said, in their yard. And the neighbor didn't even come out. And so when he went to knock on their door, because they didn't say anything to him, they said to him, I've already talked to my insurance company. My insurance company said, I'm not responsible for anything. I think being neighbors.
Yeah.
You should at least make sure he's not dead. You didn't call him.
Well, that happened to me too. So that's
What's that?
I said that happened to me before too.
Yeah.
A giant baby tree fell in my neighbor's yard, tore his room with this. He tore my stuff too, and the man came and I said, I know about him. But by him being my neighbor, I did repair the fence.
Right.
And they settled my claim, and they had to call his own insurance company and settle his claim.
Yeah.
Well, he didn't mess up his house, just his fence.
Mr. Destroy shit out there in that.
Yeah, but fortunately, no structures. The only thing was a little bit of her car. We don't know how serious because the tree's too big to tell right now, and you got to get the tree off of it before you can tell. But it doesn't look serious, super serious. But she can't get out. She can't use it anyway. That tree is huge there. The city. Oh, so finally I got to bed. It had to have been really close to midnight, and the police officer, when he came, and he was looking at things, he said, I've never seen a tree this big. And he said, this is like a movie or something. I said, yeah, a horror movie. He said, yeah. Okay. And so he was calling all the people he was supposed to call, reporting everything in. But he had to stay there because if he wasn't blocking that, they would come flying through there. And he called the people he said, now it's going to be probably a while because they got to get the tree. When I went in to do the insurance, call the insurance company, shortly my wife came in and she said, they told them it'd be an hour or two before they got out. So, and it definitely was. So we just about, we finally got to bed maybe around midnight or so, maybe a little before midnight, but still the adrenaline was so high and all the, well, what if this and what if this, and stuff. And finally I was almost about to go to sleep when the chainsaw started, in the big truck with the lift and the thing came in, and there was no sleep for that for a while. And after a while, I fell asleep even with it. My wife stayed up and watched it all. She said they filled that big old truck that they brought out there. And that was just the very top of the tree. And they pushed stuff into my neighbor's yard. The little stuff they couldn't pick up with the claw, they just pushed it and got a bobcat and just pushed it into her yard. And so anyway, it's that was last night. And then my wife just called. My wife and this lady, we're decent neighbors. We don't go to each other's houses, stuff like that, but we're on good terms and stuff. And sometime in the past, my wife and she became friends on Facebook. Well, my wife hardly ever does anything on Facebook. All she does is professional type stuff, so Julia probably doesn't pay any attention to that, or maybe doesn't even notice she does it. But Karen reads Facebook, keeps up with Facebook, so she's been watching Facebook today, and the woman's dad, who may actually still own the house, or her mom owns the house, they live in Tuscaloosa, so it may not be even in our neighbor's name, it may be in their name. And he said, oh, the tree was on your neighbor's property, so they're taking care of it, right? And so Karen's reading all this, and then she's heard, she sees all the correspondence going on there. She's not saying a word, so Julia doesn't realize Karen's seeing all this. So she's just monitoring it. And so Karen called a lawyer who lives in our neighborhood that we are friends with, not super close friends, but friends. And she had house tree damage to her house from another storm. I don't know whose yard it was from. And she also said, nope, everyone's responsible for his own property. Doesn't matter where the tree came from, it's an act of nature. So anyway, so when I went down to try to eat lunch, I saw I had a message from my wife. I wanted to find out what it was, so that's when she told me all about the Facebook stuff. So it's been quite a day. So I'm sorry we're late getting started, and now even later because I'm talking too much, but that's been what it is. So, what is today going to be like then? Well, we finished chapter 23 last time. I've both called the station, but when I called, they were on. I talked with the lady at the desk, explained what we needed. She connected me to the back, and she connected me right to where the broadcast was going on, not to their office, to the desk. So what are whispering? And I said, I'm sorry, I can hardly. You see, we're on air right now. So I couldn't find out anything then. I don't even know who I was talking with. So I hung up, and then I emailed, and then I checked David after class this morning. He was in another class, tree class, and we checked, and there's no email been responded. So I know we're not going today, obviously. Hopefully we'll be going on Tuesday, but I've got to find that out. Hopefully today. There's so many hopefuls in here that I'll find out something today, and I'll post as soon as I know. Because I told them earliest would be today, Tuesday or Thursday of next week. The very latest would be Tuesday of the following week. But I haven't heard word one back. So I'll try to find that out. Okay, so no field trip yet, but hopefully there will be one. Now, next issue is, because we did finish chapter 23, we are scheduled to have the test the last 30 minutes today. Okay?
I thought it was 20 today.
What's that? I'm sorry.
20 or 23?
23 is today. We're in 24 now. We had the test on 20 last time.
I need 20 tests.
Yeah, okay. So if you're behind on a test and you want to wait and do 23 later, you can do something. You don't have to take a test when it's, you just, we're running out of term though. So remember, you've got to get everything done before 1 week from today, because 1 week from the day is the last class day. The following Tuesday is exam day. I want to give everything back by next Thursday. Whether you turned it in or not, you got to get it all done by Thursday. Labs, tests, everything. Research papers by then too, because the following Tuesday is exam day. Okay, so that will be the last 30 minutes today. No lab today because we can't make the trip. So I'm going to continue in chapter 24. I hate to tell you this, but I've got to call the insurance company before they close. So probably we won't go much past 4 today. So what I'll do, sorry about this, I know y'all are going to be angry. You're going to be so angry at me for ending class early. But
you're going to end class early? What time early?
Well, sometime after 4, I'll give you the test and I'll go down and make the phone call. Okay, sorry.
Don't be sorry.
I'm cheating you out of your tuition dollars. I feel like I'm robbing you blind. Okay. So, let's get going on 24. Are there any questions, especially 23 or any other questions? Okay? Yeah, and you can work on that one today too. You're going to have plenty of time. Okay, let me do this while we're thinking about it. I have received 5 research papers out of 21. Okay? So I'm missing 16. Lab 1, missing 1, 2, 3, 4. Test 1, missing 1. Lab 2, second. Okay, lab 2, missing 2. Test 2, missing 2. Lab 3, that's the moon lab, I've received 6, 7, 8, 9, 10 out of 21, so almost half. Test 3, missing 1, 2, 3, 4, 5, 6. Lab 4, missing 1, 2, 3, 4, 5. Test 4, missing 1, 2, 3, 4, 5, 6, 7. Lab 5, missing more than half. Test 5, I think that's the one that had questions with it too, so I may have part of your lab, but not all the lab. Okay? Test 5, I've got more than half, but missing quite a few. Lab 6, missing 1, 2, 3, 4, 5, 6, 7. Test 6, missing, well, I've got more than half, but Lab 7, probably I have fewer than half, and Test 7, probably slightly more than half. So folks, there's nothing I want to return something to you before next Thursday. So please, if you're behind in something, get done as much as you can. Get those labs in and but I'm preaching to the choir here because y'all have probably pretty much got most of your stuff in. It's the people not here that don't have their stuff in, mostly. Yes? The lowest lab and the lowest test, but not the paper and not the final exam. Okay, those are not droppable. Okay, so any questions before we get going on today? We're in chapter 24. The section in 24, I think, is still 24:1, water on the earth, and we're talking about surface water. Okay? Now, collectively, these are the waters that are found in streams, ponds, lakes, and reservoirs. What do we mean by reservoir? A man-made lake, like Smith Lake. Just about all the lakes in Alabama are hydroelectric lakes. They have dams that man has made, and now they have the reservoirs, which are great things to have, unless, of course, that's going to cover your property. But mostly these were done back at the time when it was probably underpopulated. Probably the people who lived in those areas were fairly poor, and probably they got a pretty good deal for selling their land to whoever it was that was building the dams to do the thing. So that's where our surface water is. Okay? And much of our city drinking water comes from these kinds of places. Birmingham, I think it's Lake they get most of their water. Okay, I don't know about Bessemer. So, what are these areas? The areas called a watershed are the land area that is drained by a stream or a system of streams or rivers or creeks or whatever. Okay? That's what a watershed is. Two adjacent watersheds, these areas that drain into a common stream, that's a watershed, are separated by a divide. Doesn't have to be super high, but some sort of a high point that the water flows this way on this side, that way on the other side. Into this stream over here, then into that river over there. Okay? That's called a divide. The U.S. has one major continental divide and then another minor continental divide. A continental divide separates the watersheds draining into the opposite sides of a continent. Now, the reason I say we have one minor one is this. Okay? Here is the diagram that's in your book. These are the three biggest watersheds in the U.S. Okay? The first of these, the biggest of these, is the Mississippi River watershed. Now, it's made up of literally hundreds or thousands of smaller watersheds, but they all drain into the Mississippi and dump into the Gulf of Mexico. Okay? Now, look at the extent of this. Upstream from the Mississippi, here's the Mississippi going right up here. And then here around St. Louis, the Ohio River comes in. Mississippi keeps going further north. Now, what they don't show is, I'm sorry, that's not St. Louis here. I think St. Louis is here. At St. Louis, the Missouri River comes in. And the Missouri River is a watershed for most of this area. Oh, there's lots of major rivers that flow into the Mississippi. The Tennessee River, doesn't it? Whoa, I didn't see.
I don't think the Tennessee River flows in that.
No, I was just going to correct myself there. Antonio's here, but I saw Antonio was here. He disrupted me. Okay. No, the Tennessee River doesn't. That's why this gets cut off here. It flows into probably Mobile Bay ultimately. Okay. But I was trying to think if the Tom Bigby, Tom Bigby, I think that still flows in there. But many of the others, everything east. So that's why I said there's another minor divide. The major continental divide goes down this way. Okay? Now there's another divide here. The upper part here goes into the Columbia River watershed. The Snake River comes through Iowa, the Columbia River here. Lots of rivers feed into that. And then the Colorado River watershed is down here. Lots of rivers and streams and other things flow into that. There are plenty of other watersheds in here, but none of them are the size of these three.
All of them go to the Gulf of Mexico, right?
Okay, no. These two go to the Pacific. Okay? This one goes to the Gulf of Mexico, plus a lot you don't see. The Rio Grande goes to the Gulf of Mexico. I'm sure other rivers in Texas do. The Flint River, Altamaha River, whatever that come out of Atlanta, the Chattahoochee, which is part of the boundary between Georgia and Alabama, that flows into the Gulf of Mexico too. That's a series of watersheds. And then there's a whole bunch that flow into the Atlantic. But these are smaller, and the reason it's smaller, there is another continental divide somewhere here that everything east of it flows into the Atlantic, everything west of it flows into the Gulf of Mexico. But remember, the Gulf of Mexico goes into the Atlantic as well. So ultimately it's going to the Atlantic. But Mississippi doesn't go directly, it goes into the Gulf and then later there. There's plenty of watersheds here too, but these are the big three. Mississippi, going into the Gulf, ultimately the Atlantic, the Columbia and the Colorado, which are ultimately make it to the Pacific. Okay. Colorado watershed goes into Mexico first and then into the, what is that called, the Gulf of California here and then into the Pacific. This one goes straight into the Pacific. Okay, so those are our watersheds, the big ones. Okay, there's many smaller ones. I know there's a divide. It has to be a divide. When I'm driving home on the Western Superhighway here, leaving campus, I go up a pretty tall hill, not super tall, and then right when I crest it, I see all the city of Birmingham out there. That has to be a divide. Everything on this side goes here, and this side goes here, okay? So that has to be a divide. Summerton, Alabama is a divide. Things go one way on one side. So there's all sorts of these things. Now, I think I mentioned this to you before. Last year, when my wife and I were, a couple of summers ago, she had meetings in Salt Lake City, Utah, which is right around here. But we went early and drove up into Idaho and went into some of the areas we hadn't seen in Idaho. We went over to Yellowstone, but it was August, and boy, it was so crowded we couldn't see a lot. But we drove through the park quite a bit, and after I'd been in this and been in the course, I kept noticing the signs in Yellowstone. You're now crossing the Continental Divide. You're now crossing the continent. What we were doing is going back and forth, those roads winding through, crossing the Continental Divide over and over and over again. And so we started paying attention to it. I said, okay, Karen, look, that river is flowing north. That's going to wind up in the Pacific. Oh, this one's flowing east. That's going to wind up in the Gulf of Mexico. She said, you're kidding me. And sure enough, I mean, just a few miles apart, some of the water was going to the Pacific, some was going to the Gulf of Mexico. Because we were right passing back and forth over the Continental Divide in Yellowstone Park. Several times. Of course, we were going various directions there, and the Continental Divide does that kind of stuff too. So those are your watersheds. Smaller watersheds, like in Georgia, there's the Savannah River here. I grew up in Georgia, so I know Briar Creek feeds into the Savannah River. That's a watershed. There's the Mulgee, the Oconee. There's just all these rivers. The Flint River over here. These flowed into the Gulf. The Atlantic. These flowed into the Gulf. Okay? Each of those was its own watershed. But then smaller creeks had their own watershed. So every stream that drains a certain area, that's a watershed. And then when the streams go together to form a river, all those are in that river's watershed. So they just sort of multiply. Okay. There's, like I said, hundreds, if not thousands, of watersheds in the Mississippi River watershed. Maybe tens of thousands, I don't know. Okay. And the divides are the things that separate the watersheds. Okay, that was surface water. Groundwater. This is underground water. It's short for underground water that's saturating the open spaces between the rock and the soil particles. Okay? Now, where is the groundwater now? Probably right beneath the surface, because just about all the soils are almost completely saturated. But normally the groundwater is down at a level, I don't know, well, let's see, it says here, percolates downward from the surface. Now this is surprising to me. 25 times larger than the supply than the surface fresh water. If you think of all the lakes, all the rivers, all the ponds, all the streams, everything that we have on the surface, 25 times that is underneath the ground. Okay? 25 times larger supply than the surface fresh water. Now, here's what I was getting at. often within 100 meters of the surface. 100 meters is something like 300 and some odd feet, okay? That's fairly deep, okay? But this is sort of an average within the nation. This guy that wrote the book is from Arizona, where it's pretty dry. So their water table is way, way down there, okay? So that's why he says within 100 meters of the surface.
Yeah, that's it, the aquifilters.
Aquifers, yeah. That's what you're getting into, and we're going to talk about that a little bit later.
How can that stay so clean? They say that aquifilter water is cleaner than surface water.
Oh, absolutely. Because you see, it all percolates down from the surface. And when you go down 100 meters, that's a football field down. And the soils are good friends of ours, right? We love our soils. They are filtering. If you go to the Birmingham Water Works, I'm guessing this, I haven't been there. I bet you the first thing they do is filter it through sand. That is the first stage. You get a lot of the junk out of it, just filtering it through sand. And just think of a football field deep worth of sand and other materials that you're filtering through. You're taking out most of everything then. Yeah, so yeah, those
all the chemicals and everything else, wouldn't it?
a lot of times, yes, because they're going through clay particles. Clay particles have those very highly reactive surfaces. They grab whatever they can. Most of it that makes their way through, pretty pure water. Okay? Not quite the same as distilled water or something like that, but still very, very pure. The surface water is filled with bacteria and chemicals and pollutants and everything. They have to process to get those out, whereas a football field deep of soil filters that out for you. So most of the time, that groundwater is, if it's deep groundwater.
Right.
Now, this may not be an aquifer even at 100 meters.
Yeah.
When my dad had them drill the first well on the pond, even before we moved down to on the farm, before we even moved down to the farm, we were living 7 miles away and he was driving there. Had him drill the first well so he could water the cattle. Okay? I think he hit water right around, it seems like 100 feet or so, maybe 125. Okay? Good water too. My goodness, that was good water. At only 100 feet or so. Okay. Later, that well dried up. What happened? Surrounding farmers started irrigating like crazy, drawing down the water table. Now the groundwater was deeper. Okay? And we had some very dry years there, like decades of dry years. So those were really full, and not as much. Say again?
The table had dropped down pretty low.
Yeah, and then too, there wasn't as much filling up because we weren't getting the rainfall. Well, when we drilled the well at the place where we built a house over on the farm, I'm thinking they hit water shortly after 150 to 200 feet, but it wasn't sustainable because they pump it for 24 hours, and if it runs out, then that's not good. So they had to keep going. And they went down about 250 feet, which is awfully close to our 100 meters here, before they hit good sustainable water. And it is good water. It's really, really good water. Now, we don't have that much limestone around. They say the limestone water is really sweet water. But it could be that far down, there is limestone.
We have limestone on this side.
All over the place, yeah. So I would think most of the wells here would be pretty good. Now, we had a well up at Smith Lake. My parents-in-law had a place up at Smith Lake, and they had a well, and I almost always got my stomach messed up every time I went. We hauled water. What it was just the lake water filtering horizontally over to the well and dumping into it. It wasn't getting the filter through here. It was surface water, groundwater, untreated. Surface water, untreated surface water. It messed with me.
If he'd have dug a well, he still probably got the same water, probably, wouldn't he?
What's that again?
If he'd have dug a well on that property with that lake lake being so close, he probably still would have got the same water.
That's what I'm saying. That's what he was getting. He did drill a well, and it was getting just lake water.
Yeah.
So it was.
Not enough.
It didn't. And our neighbor, when we expanded the house, we had to move our septic system, and it got close to theirs, their well. And I said, they say for us to do the septic system like that, you're going to have to put. Well, by that time we had gotten county or city water at the lake, and I told him, and he was on that. I said, you're going to have to cap your well, even though you're not using it. He said, help yourself. That water was so filthy, it's just stank. We're never going to drink that water again. Help yourself, and we capped the well for it. So anyway, that's groundwater. Now, not all groundwater is what you're describing all that good.
Right.
When you get down to aquifers, that's when it's really good. Okay. And we'll talk about another term for it. So, what's the groundwater flow? First stage, it goes through sand and gravel. Sand and gravel has open pore spaces, very permeable to water flow. Now, gravel doesn't get out much. Because gravel is big size, the pores between gravel is big. So water just goes right through that. Sand, smaller size, but still water goes through it pretty easily. Very permeable to water flow. But then you hit your clays. The clays, now this is not quite accurate. It's close, but not quite. They say low porosity. What they should be saying is small porosity. In other words, you have plenty. In fact, in a typical clay soil, a tillable, good clay soil, you're going to have maybe more porosity than you do in sands, but the pores are so tiny because the clay particles are so tiny. But you have gazillions of them, so you do have good porosity, but it's just they're so small. Well, this is where I make the example of, have you ever been to a fast food place in the morning on your way in or something, and you get one of those hot cups of coffee, and they give you that little swizzle stick that you stir it with, and you can sip on that to see if the coffee's too hot to drink, right? You've probably done that, right? You probably don't get a lot of coffee when you suck on that, but you get some, right? Just enough to tell, so you won't burn your mouth so bad. Now, if you imagine going back later in the day and getting a milkshake there, and they gave you a little swizzle stick to use, what chance have you got of getting the milkshake through there? Yes, you're not. You're going to pop your ear, go trying, but you're not going to get it out, okay? So, that's what clays are. The pore sizes are so incredibly small, it's like sucking a milkshake through a very small capillary tube. You're not going to do it. Or even sucking water through one. It's not going to happen. And that's indeed what the plant roots are doing. They're trying to pull the water out. And the clay particle is, no, we got that water, Sand, no problem. Clays, big problem. Yeah.
So is that why people have iron and they have a clay? They put sand in it.
Okay, sand is one thing you could mix with it, and that would be a bad idea. Far better is to mix that humus, your leaf mulch, and that kind of stuff. Because that sand, water will go right through that, but the leaf mulch, it loosens the clay, but also gives up the water pretty easily to the plant roots. I would go with that if I could. If you can't, sand is next best. Yeah. Okay? This part is good. Impermeable when saturated or compressed. Now, saturated means got a lot of water in it already, like they are right now. No water is going to get through because just like that thin little thing you're sucking on, you can't get much through it. If you suck hard enough, you can, but yeah, it's just going to be very slow or compressed. Now, if a clay is compressed, like you run a car over it or equipment over it or something like that, you press it down. Clay particles tend to be in sheets, okay? And when you run over them with something, especially when they're wet, they squeeze together, force the water out. You close all the pore spaces. Now you have low porosity and very small porosity. You have both when the clay particles are compressed. So if you've ever been on a dirt road that had mud puddles, that's probably why it has mud puddles. Probably the clay in the bottom has been compressed so tightly, it's not letting the water seep through. Their water is standing in the mud puddle, and why isn't it seeping through? The clays have been compressed, and you do have low porosity. Then you have impermeability just because they're both saturated and compressed. Okay, that's groundwater flow. Here's the illustration of that. When you have the large particles, sand or gravel, you also have large pores, and the water just goes right through. Okay? But when you have the small particles, like clay, and they sort of show them as flat, though they show them in all orientations here, you have lots of pore space here. It's just that it's not well connected. You see, the water may go down this way, but then run into a thing, and it has a hard time finding its way through. You call that tortuosity. It's a tortuous pattern to get through there. Even though there may be plenty of porosity there, it's so small, such small pores and blockages that it's hard for the water to get through. Now, it doesn't sit up there on top. It'll come down in here and here and here, but then it'll get stuck here and here and here, and it's hard to make its way through. That's what the problem with clay. Then you run over it, they all flatten out this way, and now you've got a solid sheet there. Even though you've got plenty of pore space underneath it, you can't get through that top layer.
Let me ask a dumb question.
No such thing.
What makes lakes maintain that water? Is it a clay basin under it or something that makes it hold that water instead of draining out of it, or they got water coming back in from a spring or something?
Yes to both, sort of, okay? A lot of times your subsoils are high clay content. So if they dug out the lake, you're probably into the subsoil. So now, unless it's a rocky subsoil, that would be sort of porous. But at first I thought you were going to say the dams. My dad did put a dam on one of the creeks that went through the farm, so he could water the cattle there in that field as well. And then we could have fishing and that kind of stuff too. But when they built the dam, they brought in a special kind of clay called bentonite clay. It's a swelling clay, like the clays down in the Black Belt of Alabama. We talked about those. They shrink as well. Well, because the dam always has water on this side, that clay stayed wet. It would swell up, and it basically plugged it down. So there was very little water that made it through there. Because the core of that, they put that bentonite clay in. So that's part of it. The other part is when you're above what they call the fall line, which would be probably a line around Montgomery to Selma and stuff like this. Below that, you can almost dig a hole, and if you got clay in the bottom, it'll fill up and you can have a lake. Above the fall line, where you have enough fall going on, it's hard to have a lake unless you have a dam on it, okay? And a supply.
Yeah.
So what you were saying before, you need supply in to make up for that you lose.
I got you.
So both of those are very essential. Okay. Now, what are our groundwater deposits and how are they put together? Well, one is called the zone of saturation. This is collected groundwater above some impermeable layer. Could be a clay layer, it could be a rock layer, okay? Could be a granite over in Georgia, or something that water just cannot go through, or it goes through incredibly slowly. So it collects the groundwater above that layer in the pore space of the soil and gravel particles that are up there. The water table is usually the top boundary of that zone of saturation. And that's what we were talking about when you had droughts and not enough recharge. the groundwater table starts sinking. When you have irrigation systems sucking that water out, the groundwater keeps sinking. Nowadays, that groundwater is coming pretty close to the surface. Well, not that close, but this top layer of the zone of saturation is rising. Okay? The water can move laterally within the zone of saturation, and it does. Okay? Most of the time water goes downhill, but it can go laterally anywhere in that zone of saturation. Now, what you were mentioning before, your aquifers. These are subsurface layers of highly permeable material. Think gravel, think sand, capable, now this is so silly, highly permeable material capable of producing water. It doesn't produce water, it allows the water to flow through it. So in that sense, I guess, is producing it. But water comes from water. It doesn't come from highly permeable material. And what our artesian aquifer is confined under pressure from water at higher elevation. Now here's some illustrations of this. And these are sort of good. This is not showing, well, it sort of is. Somewhere down here you have an impermeable layer. And this could be bedrock down here. It could be almost solid rock or incredibly dense surface layers of, say, a subsoil or something like that. Above that you have a more permeable soil that holds water in the pore spaces. Pore spaces are the key there, okay? Now, just as above ground, water tends to go downhill, okay? And as long as you have a layer like this, it's going to find its way to go downhill if possible. Now, if on its way it hits a depression, like you said, a lake or something, and it gets below that, you don't see any water coming in, it's coming in from the bottom. So this could be a lake that is being fed by groundwater, by saturated groundwater, yeah, okay? Whereas the water table is here it's going downhill. Now, sometimes you have this groundwater that finds its way out and makes what they call a spring, okay? Springs could be, usually are from an aquifer. They could be artesian or not, okay? The really pure water is artesian, okay? Sometimes the springs are just groundwater, okay? That may not be that deep, okay? Or you could have a river running through here and the top surface of the river is even with the saturated, because the banks of the river are higher on either side, and on either side you have unsaturated soil, but you also have the river flowing, and it's below the water table. Or in very flat areas you have a swamp. And especially down near deltas, remember we talked about those in an earlier chapter, near the coast you have a lot of swampy area because you're below the water table there. And even in dry seasons it seems to always have some water there. The house that my folks built in Georgia had a swampy area on one side and a swampy area across the field on the other side. And my mom rued the day that they built between two swamps because she hated mosquitoes. And boy, did they have mosquitoes, okay? Because the swamps were great breeding grounds for them. Open water like a pond or something like that with fish, they tend to eat the mosquito larvae. Swamps, there's not much of anything that's going to stop them. She fought with those mosquitoes as long as she lived, and she really didn't like them at all. But ultimately, all the water, even this groundwater you never see, sometimes will make it to the ocean because it goes through that permeable layer right into the ocean. The river ultimately going to go to the ocean. The swamps will ultimately drain to the ocean, but sometimes your groundwater drains directly to the ocean. So the artesian aquifer, that's what the next slide I think is going to show. Yeah. What you have here, and this is still a strange, there's something wrong with this picture, okay? They show the artesian aquifer is opening up to the ground. That's usually not the case. Usually it stays below ground, but this is the water table here. They have water above the water table, which doesn't make sense, okay? So the artist just got this a little wrong. It should be coming in like this and then going down. And if it reaches, and maybe they mean that, I don't know, I can't tell what they mean by this. Maybe the hill is supposed to continue here and they just cut it away. I don't know. But anyway, you have water at a high elevation here, but down here it's at lower elevation. Well, water seeks its own level. So if you drill a well here, you may hit artesian aquifer. The aquifer is really down here, but if you drill the well, the water comes all the way up to there, okay? And as long as you don't have huge fluctuations in it, you can pump water just from here and have really great water. Now, some places will be below the pressure surface of the water table way back here, and the aquifer, if it finds a way up, it does what we call an artesian well, artesian spring, a flowing well. They have lots of names like this. There was one, the next county down from where I grew up, Millen, Georgia, had Magnolia Springs was the name of that place. It had swimming there. They didn't have to treat the water. There was an artesian aquifer coming up, always flowing out, and we went swimming there a few times in the summer. That water was cold because it was around 70 degrees. Because everything, if you go deep enough, that water is around 70 degrees. Okay? Now, I didn't realize it at the time, but when I was in high school, the farmer that was catty-cornered across the crossroad from us, he was getting out of the cattle business because he was losing money or not making as much as he wanted to. And he found out that this was in Vietnam time. And in Vietnam, we found out we were pretty ill-equipped to set up camps and places in really rugged terrain. We had been used to fighting wars where everything was pretty organized. Vietnam, it wasn't. So the Army, Fort Gordon is just in Augusta, not far from us, they wanted to train their soldiers to set up out in the boonies. He found out they were looking. He offered his farm, which was pretty hilly. It had been used for pasture, for them to set up their camps and to have to rough it, out there. And they didn't. They had to bring in tanks of water because he didn't have a source of water there. And they would have the tanks, and they would take showers under the tank to have the tanks up in supports and have gravity flow. And they had to kind of rough it. But then they found out just a few miles from where he was, just down Story Mill Road, from where and basically they were setting up a landing strip there for cargo planes to come in and to go out, and so training the pilots to be able to land on uneven terrain and that kind of stuff. I remember the first night they started air operations, the night operations, where they had to fly by instrument flight only, I think is what they call it. Their flight pattern went right above our house. And all night long that first night, every time one took off, I was awake. And I thought, this is going to be a long summer. But the second night, I slept through them all. Okay, I got used to them, and not much except trees falling and stuff like that bothers my sleep, okay? But anyway, They found out that just down the road from where they had their landing strip and stuff like this, less than probably a mile or less than 2 miles anyway, there was a low area where there's a creek. McBean Creek went through there, but feeding into the creek was an artesian well. Now that artesian well was about 70-degree water. And guess what? In the wintertime, that felt nice. And in summertime, that felt nice.
Yeah.
But in opposite directions. In the summer when it was 90 out, that was a good shower, you know. And in the wintertime when it was 40 out, that was a good shower, you know. And they leased, that was not owned by the same guy. They went over there and leased the flowing well. They set up the showers there. The water was better, purer. They probably drank as much of it as they could too. It felt a lot better than being out of the tank. And anyway, so there are these flowing wells that are artesian wells. That artesian water is good stuff. That's what we were talking about before. You don't need to filter.
What was China used to use back in the day when we were kids? Artesian water. They
Yeah.
used to drill wells and make moonshine out of that water.
Uh-huh.
Always had to be near water to
Right.
exit and draw.
Right. Well, I wouldn't know about that. No. Okay. No, actually, my uncle swore that he found where a former sharecropper had a still on our property, and boy, that kept us kids for the next several years. We searched every high and low, seeing if we could find where that still had been. He never told us where it was, and we never found it, but it kept us occupied. Every Sunday afternoon when we didn't have work to do, we were down there in the woods looking for that still. Okay. But it long since gone. All right. Fresh water as a resource. Let's just keep up with where we are. I'm sort of skipped over example 24.1. If on an annual basis precipitation in a watershed is 914 millimeters, the actual evapotranspiration, that's both evaporation and transpiration, which is the plants sucking the water out of the soil and then sending it up, into the air, or evaporation is just evaporating from the surface, is 786 millimeters. 70% of the surplus precipitation is runoff. What is the percent? They just are playing with numbers, so let's not mess with that. You can read that. It's really an interesting problem. Then it said if the watershed area described here is described above is 12 square kilometers, what is the actual volume of that? So you would have to know whether that's not worth even reading. Okay. All right. So freshwater is a resource, page 613. Oh no, in your book, 24-8. Okay, that's where we are. Now, fresh water is required for life processes. Every kind of life process. Okay? Also for modern industrial society. It's a necessity. Absolute necessity. When I was in the Navy, you're surrounded by seawater. You couldn't drink seawater. Every ship, major ship, now the old sailing ships, they didn't have it. They had to carry their own water. And they also carried their own beer too, but that was back before the modern Navy, okay? Sometimes they would have to replenish the beer quite often and hardly ever have to replenish the water, but that's a different story, a Navy story, okay? And here is Rakiria.
Yeah.
Donald. And Shikaya. Turn around and leave it. Okay. All righty, good deal. All right. Freshwater absolutely required. When I was in the Navy, most ships that had machine driven, they used some of the steam. Well, okay. some of the heat energy they had from burning in the boiler, the fuels and stuff like this, they actually evaporated water and then caught it and distilled that water and then used that as fresh water. The very purest of that distilled water went to feed the boilers because you didn't want any contaminants in the boiler. They could destroy your boiler, your turbines, steam turbines. Then you couldn't move. The crew got secondary water, any water that wasn't quite as well distilled. That's what we got to drink, okay? But we had to have it. Good deal, thank you. All right. So it's absolutely necessary. And maybe you knew you had to have it, okay? Now this, to me, is absolutely remarkable number. The average U.S. usage for fresh water, okay, is 570 liters per person per day. Now, a liter is a little bit more than a quart. So divide that by 4. If someone's got a calculator, divide 570 by 4. 570 divided by 4. Second? 142.5 gallons per day. Any of you drink 142 gallons a day? No, you'd be in the restroom all. I know. I mean, you couldn't do it. Okay. So how in the world they get this? Well, 40% of that is used in agriculture. You're not using it, but every bit of food you eat required water to grow. Every animal product you ate required water to grow. Okay. 40% is for production of electricity. Now, most of our electricity is produced by other sources like coal or natural gas or something like that, but still quite a bit of it is used for hydroelectric. So 40% of fresh water is used for that. 10% industrial, okay, which we take advantage of as well, and then the remaining 10% is what we actually consume. But, that does count showers, flushing toilets, washing dishes, washing clothes, all those uses of water, plus what we drink. But 570 liters per day is what the average U.S. usage is. And I can almost guarantee you we lead the world in this because we are water hogs. We are not very good at conserving anything because we got plenty of fresh water. Not many nations in the world have that luxury. We do, and we waste like crazy. Okay. Most of the supply comes from surface water, even though way more water is in groundwater than in surface water. The surface water is easy to get. It's right there. You don't have to pump it very far. Okay? The bad news is there's more sediments in it, there's more bacteria in it, there's more pollutants in it. So you have to purify. So we have our water plants that do this. That artesian water that we pump out of the ground at the farm, boy, does that taste good, and it doesn't have a bit of antifungal, antibacterial, it has a little bit of sediment perhaps. Older brother's well, it gets a lot of sand in it, but, so he has to have a filter for that. But ours is just in really good shape. Now, all this, though, depends on precipitation. If y'all remember back a few years, when Lake Purdy got down to maybe 15% or something like that, huh? It was, we were really getting close to having very severe water rationing. Okay? If you read about places, the one state that has the most water of any in the country is Florida. And yet, Miami, the city that it is sucking so much water out of the Everglades we're destroying a natural resource there. And now there's big moves to try to replenish the Everglades and try to divert and get more water from somewhere else for.
So you mean to tell me the city of Miami is sucking the Everglades? That's their water supply?
That has been their water supply for years. And they are doing a terrible job of draining that, okay? Out west where it's really dry, city of Los Angeles brings their water from the Colorado River, that big lake there, is it Lake Mead? I believe it is, and brings that. And back a few years ago when they were having such droughts, Lake Mead was getting to dangerously low levels. That's one deep, big, enormous lake. In fact, isn't that the one behind Hoover Dam, which at one time was the largest dam in the world? I think the Chinese have built one bigger, but Hoover Dam is still a massive, massive dam. And back during World War II, when they were training pilots very, very rapidly, because a lot of them were getting shot out of the sky and crashing and doing other things, they would use some of those river valleys to do their training in. And there was a plane that went down in Lake Mead. And it went so far down, because it was so deep, they never recovered it. And it just wasn't going to be worthwhile. So it stayed down there. When the drought was so severe there, the water got down, they discovered that plane they had almost forgotten about, because the water got that low in one of the biggest reservoirs in the U.S. Okay. So anyway, the surface water depends on precipitation. More than 40% of our water supply comes from the groundwater. So 60% approximately comes from surface water, about 40% from groundwater. The good news there, as you were saying before, relatively free of bacteria, relatively free of suspended particles, so you don't have to treat it. And it's good water most of the time, okay? However, you do have to pump it to the surface. And the deeper it is, the more energy you spend pumping. So the trade-off is, do you spend your money cleaning up the surface water or pumping up the groundwater? But even when you pump up the groundwater to serve communities and stuff, because it gets into surface lines and stuff, you still have to treat it, because it'll pick up bacteria, in the pipes and stuff. Now, we don't have time, and it's not really the place here, but does the name of the city, Flint, Michigan,
Yes.
bring something to mind?
Of course.
Somebody there decided they were going to save some money. And they were going to divert and not use their groundwater and start using more surface water from a very polluted river. And they thought their regular plant purification was going to fix that. It didn't come close. And they started getting some terrible water, terrible pollutants, terrible sicknesses, and they polluted all their piping and stuff like this. So even pipes and stuff that were in pretty good shape now were all contaminated.
So everything in Flint, Michigan got to be dug up and redone again.
That's exactly right. Because someone's trying to save you.
Yeah.
Guess how much? Ooh, how many lives, how much
Right.
health, and how much money they lost by having to dig all that back up.
The health consequences was real bad.
Oh, absolutely. That's the worst.
And they had lead, was lead in that water.
Yeah. And that's not an easy thing to get out of the water either. Okay. And the worst thing is, really bad thing anyway, is that sometimes lead poisoning goes undetected
For a long time.
for a long time. And
it's just-
yes, young kids with it, they start getting developmental disorders. No one can explain why until they do some blood work and find out their lead levels are just way, way too high. And how do you filter that out? That's a terrible situation. Okay. Now, seawater, we got plenty of that. 70% of the earth is covered with seawater. Now get this, with an average depth of 3,800 meters. 3,800 meters. Now, just to get an idea, 1,600 meters is considered to be 1 mile. Pretty close to 1 mile. Not exactly, pretty close. 16 will go into 38 more than 2 times. So basically you're talking about average depth of more than 2 miles. 2 miles deep. Not many of us really want to walk 2 miles on a flat surface. Just imagine 2 miles down. And that's average. You have some real shallow water, and then you have some really deep water. 70% of the earth is covered with seawater at an average of 3,800 meters deep. 30% of the earth is dry land, because 70% is water, with an average altitude above sea level, average is only 830 meters. So what's underwater is way deeper than what is high above land. You could bury the Himalayas in several places in the ocean. I mean, there's that big a difference. Most of the ocean is still unexplored. We have decent ideas about just little bits and pieces of it. And I've heard the saying many times before, we know more about outer space than we do about our own oceans, because they're hard to study. They're dark, they're cold, they're otherworldly almost. I mean, they just are absolutely amazing. Okay. Before we move on, I probably should have done this before. I just noticed there is a table in your book on table 24.1. This is back on freshwater as a resource. On your page 24-8, the average individual freshwater usage in the home. This is not talking about agriculture, industrial, hydroelectric, or anything else. This is just that 10% you use in your home. Toilet flushing is about 1/4 of it. Okay? Clothes washing, about 1/5 of it. Showering, about 1/6 of it. Just running the faucet for various things, that could be washing dishes and washing your hands and that kind of stuff. About 15.7, a little less than 1/6 of it. And then the sad part is leaks and others. Just places you have water wasted. That you're not just running in the faucet that wasted, that's almost 1/5 of it. That's amazing. Okay? We're water hogs. We really are. Okay? Again, sort of catching up where we are. On your pages 24.9 and 24.10, you have 2 pages here of water quality and wastewater treatment. And one of the first things you see there is a grit chamber. Oh, he just stepped out. I was going to point that out to Jerome, that's the first step in filtering. Okay? It's well worth a read. It's pretty enlightening what you've got there. Okay? Page 24-11, you see a wastewater treatment plant. Well, wait, I don't know if that's wastewater or not. That may be surface water that you're treating before you pipe it into people's homes. So this isn't wastewater. But before we get to 24.2, this is somewhat of a sobering thought. Whether you're getting your water from artesian water, from groundwater, from surface water, or whatever, guess what? We are recycling water all the time. Okay? Because guess what? There's not that much new water ever being created. Except for what? Oh, but no. What it rains is stuff that's evaporated out of the ocean and come back over land and drop. It's the same water. It's just being recycled. So guess what? Upstream and say Birmingham's waterworks and wastewater treatment and stuff, the residue from that goes back into the river. After they cleaned it up as much as they can, it goes downstream, and that becomes somebody else's freshwater. And then they use it, and it goes wastewater, they treat it, send it on downstream. That becomes somebody. So unless you're at the top of the hill, you know, water isn't the only thing that flows downhill. Never mind, we won't go there. Okay, you shouldn't know that. Okay, all right. So let's get back. Here was the seawater, and we mentioned most of the ocean still unexplored. So let's look at some of these saltwater resources. They start with oceans and seas. The ocean is a continuous body of water covering large parts of the Earth's surface. 3 principal ocean regions. Why they put them in this order, I don't know. It isn't even alphabetic, you know, but the Atlantic Ocean, maybe that's the one, I don't know why they put it here. The Atlantic Ocean is the second largest ocean on the book. It's actually getting bigger because of the diverging plates there, but not very fast, okay? Very slowly. The Pacific Ocean is the largest and also has the greatest depth. The deepest part of the Pacific Ocean is something we'll talk about later, the Marianas Trench, okay? Very largest, way larger than anything. In fact, I'd say probably almost half of the ocean water, maybe more, is in the Pacific. And then the Indian Ocean is the smallest surface area, smaller than the Atlantic, but still a good sized thing. Let me get my handy dandy visual aid, just so you'll get an idea of the relative size. There, my folks, is the Pacific. Almost all you can see from this perspective, right? The Atlantic, still pretty big, but there's lots of land on either side. The Indian is here. Again, a pretty good sized ocean, okay? But not as big as the Atlantic, and definitely not as big as the Pacific, okay? So those are the 3 major oceans, okay? Now what is a sea? Oceans and seas. A sea is a smaller region distinguished by special characteristics. Now, various things are called sea, or called by different names, but they're all considered a sea. One of probably the most well-known is the Mediterranean Sea. That's what separates Africa from Europe, the Mediterranean. Lots of civilizations started around the Mediterranean. Egypt was up near the Mediterranean. All the European, the Roman Empire, the Ottoman Empire, there's just a lot of activity around the Mediterranean. A big sea, okay? Now, even though it's not called a sea, our Gulf of Mexico, by definition, is a sea, okay? It's almost completely surrounded by land, but has ocean input and output, okay? The Caribbean Sea, real close to the Gulf of Mexico, the Gulf of Mexico is surrounded basically by the U.S. from Florida around to Texas, Mexico, Yucatan Peninsula, and then on over to Cuba and stuff. That pretty much surrounds the Gulf of Mexico. Not completely. There's inflow and outflow, plenty of that. The Caribbean Sea, on the other hand, is most of the rest of Central America, the northern part of South America and the island arcs that are around there, including Hispaniola, which is the island that's split up between Haiti and Dominican Republic, Puerto Rico over here, and Cuba here. Oh, the island I couldn't think of the other week, other time, was Jamaica. That's that island south of Cuba. I forgot where it was. Okay? Those are some of the seas. There are plenty of other seas. Just grab your globe and look. Hudson Bay would be considered a sea, I think, in most cases. There's the Baffin Bay up here, which would be considered a sea. There's the North Sea that's in between England and Scandinavia and the north part of Europe. There's the Baltic Sea, the Gulf of Rothnina or something like that. There's the Barents Sea. There's all sorts of seas all over the place here. Red Sea down here, a biblical thing. The Persian Gulf is a sea. The Caspian Sea, the Black Sea. Okay, I mentioned the Baltic Sea. Just go around and you'll see seas all over the place here. Sea of Oshkosh or something like that. The Bering Sea that's inside the Aleutian Islands. There's just all kinds of seas throughout. So what? Okay, the ocean is just huge areas. The seas are kind of isolated. They're smaller, and they've generally got some sort of barrier around them. Not a solid barrier, but like the Mediterranean, the Gulf of Mexico. It's almost surrounded by land, not quite. The ocean, no, mostly water. It is surrounded by land, but at way bigger boundaries. Okay. The sea is just a smaller area distinguished by special characteristics. Okay. And here again are some of those seas, and this is one right from your book. Okay. And it lists several of the seas. The Bering Sea up here inside the Aleutian Island chain. Mediterranean Sea here. The Black Sea here, Caspian Sea there. Surprised they don't name some of these others. The Weddell Sea down here off Antarctica. I can't read that one, but it's another one of the seas down there. Ross Sea, okay? It's hard to see on Antarctica because it's spread out way too big, so the seas aren't as distinct. Sea of Japan up here between Japan and the rest of Eastern Asia. So there are the seas. The oceans here, Pacific, when you put it together, it would be huge. Atlantic and Indian here. Plenty of other seas in there too. They just list a few of them. All right. Any questions? Okay. Now, this is sort of an interesting breakdown that they have, and they have a couple of errors on the slides. They have it correctly in the book, but a few errors in the slides. The nature of seawater. Seawater. What's the other name we usually use for it? Salt water. There's a reason for that. It's salty, okay? It's not something you can drink. Does anyone know why you can't drink seawater and satisfy your thirst?
Because the salt will dehydrate.
It's what?
The salt will dehydrate.
Salt.
What about the salt?
It'll dehydrate you.
Yes, actually you drink it and it dehydrates you. And here's why. Your system is constantly processing stuff. You're burning carbohydrates and fats. You're processing proteins. You're doing all sorts of stuff. And you build up salts within your system. And you need fresh water because your cells have these things called vacuoles in them. They're sort of bubbles, you might think, and they're surrounded by a membrane, and the membranes are what they call semi-permeable. It lets water flow one direction, but doesn't let salt flow the other direction. And when these vacuoles fill up, they evacuate, okay? And that's what goes into your wastewater, okay? Which is salty, okay? You have to be able to produce it. You need to take in fresh water because you need that difference in concentrations of salts, okay? Now, if you try to drink salt water, you're taking in water that's as salty as your water you're trying, and you may actually be saltier. And now, just like Tiffany said, you are dehydrating yourself because now you're losing your water to that because that is trying to dilute the water that's there. Okay? So you can't drink seawater or salt water. Okay? Now, salinity, that's the amount of salt that's there. The mass of salt dissolved per kilogram of seawater. Mass of salt, that's how they define salinity. Now, it doesn't change much with changes in water temperature. You know it's got to change a little bit because the warmer waters will dissolve more salts than the cooler waters. But overall, it's not a huge change. Now, here's where the error comes in. It says here it averages 35% with a 32 to 36% range. Impossible. What these should be, and they're correct in your book, they're just not right on the slide set, is these are not percents, these are per thousands. Okay? So I'm going to pull up a blue marker here if I can. Okay? It's per thousand. Okay? Not percent. Percent is per hundred. Okay? This is per thousand. Because you see, if you go back up here, the mass of salt in grams per every kilogram of salt water or seawater. Okay? Kilogram is 1,000 grams. So this is how many grams per 1,000 grams. So that's why it should be 35, not percent, per 1,000. 35 grams of salt for every 1,000 or kilogram of water. 1,000 grams or 1 kilogram of water. So those should not be percent signs. There are a circle above the diagonal and 2 circles below it. Percent is 1 circle below it. Per 1,000 is 2 circles below it. Okay? Now, the concentration is increased by evaporation and ice formation. Evaporation only basically evaporates pure water. So therefore the salts are left behind. Okay? Ice generally only freezes pure water, leaving the salts behind. Now some salt does get trapped in the ice, but it's not very much of it. Okay? That's what increases that. The temperature overall doesn't change a lot, except the higher the temperature, the more you have evaporation. So, and the lower the temperature, you get more ice formation. So it sort of goes both ways there. So that's why it balances out. But it's decreased by heavy precipitation, because the rainfall that falls, that's pure water. Okay? There was a movie, well, actually the book was better. In fact, I never saw the movie, but I know the book was better. If I could remember the name of it now, it was a story of a guy named, started with Z. He was an Olympic runner. And he ran in the 36 Olympics. That was the Olympics that were held in Berlin when the Nazis were in charge before World War II. And they were so proud of the Aryan race and how they were going to dominate everything. That was also the Olympics that good old, wasn't he an Alabamian? Say again?
Jesse Owens. Jesse Owens.
Jesse Owens, exactly. Ran and just stomped the mud out of him.
Yeah.
And showed the Aryan race who could really run. Okay. But also this guy, I wish I could remember his name. Like I said, it started with Z. He definitely wasn't Aryan, okay. But he ran quite well too. He had a pretty bad accident and still ran incredibly well. But anyway, why did I get off on that? I forgot now. Yeah. Oh, yeah, I know. He became a pilot in World War II. And he was flying one of the worst planes we had ever created. I can't remember its name, B-24 or something like that. Not a very reliable plane. They went down way too easily. They were tough to do in rough weather, and it was just bad. And his plane went down. And he and one or two of his crewmates that survived the crash were in a lifeboat. And they set a record for being at sea for the longest time that anyone else had ever done. Okay? They could not drink salt water. One guy did, he died and from dehydration. Yeah. But the other two made it, only to be rescued by the Japanese.
Mm.
And then they went from being shipwrecked to prisoners of war, which was just about as bad. And but anyway, that story that he had when he was at sea, and you get it in the book. I don't know how it was in the movie. I never got to see the movie. But they would capture rainwater when it would rain, and that's what they were able to live on drinking, because they could not drink that salt water. And there were days when it didn't rain, so they would get terribly messed up because their body was over salted, you might say. They could not get rid of their excess salts. And basically they were same thing as drinking salt water, you could get dehydrated big time. Okay, but anyway, that reminds me of that. Decreased by heavy precipitation. Also ice melting, which is also changing things too, and river inflow. And especially when they have flooding in the U.S., like, what was it, a couple of springs ago, was it? They had such heavy rainfalls in the Midwest and stuff. The Mississippi was just running at flood stage week after week after week, and that really messed up the salinity in the mouth of the Gulf of Mexico, and lots of the fishing and shrimping and other things got totally messed up because of excess precipitation, especially at river inflow. Now, the proportion of the ions remain relatively constant. Now, what is an ion? Do you remember? An atom is a neutral, is neutrally charged. Same number of electrons as protons. A molecule is neutrally charged. Same number of atoms as electrons as protons. But when they get out of balance, like excess electrons, then you become a negative ion. No longer an atom or a molecule, but an ion. When you get deficit of electrons, you become a positive ion, or rather than neutral. So the ions, and most salts are made up of ions. Sodium is a positive ion, chloride is a negative ion. They go together to make regular salt. Potassium chloride, magnesium chloride, magnesium nitrate. I mean, just all sorts of different salts you can have. But the proportion of ions remain relatively constant. Also contains dissolved gases. Lots of nitrogen and oxygen near the surface, where the waves mix up and stuff. That's why the fish live near the surface, because they get enough oxygen there. But you also have large amounts of CO2. The deeper you go in the ocean, then the less oxygen you have, the more carbon dioxide, because the fish, just like us, breathe in oxygen, breathe out carbon dioxide. So you get that imbalance happening there. Now, there are green plants that live in the ocean too, especially in shallow water. Those green plants take in carbon dioxide and expel oxygen, just like our green plants out here. But when you get really deep, there's not enough light to support them, don't have it anymore. So the large amounts of CO2 increase as you go down. Frankly, as those concentrations of CO2 increase as you go down, that's why you form your limestones, your carbonates, because they come out of solution when they get really cold, really deep, and really large concentration. And that forms your carbonates. Sodium carbonate, magnesium carbonate, calcium carbonate. Here are those ions. And again, there's a couple of little misprints here. Nothing too serious, but there are some misprints. I want to point them out to you. Chloride ions are the largest percentage by weight. Second is sodium. Sodium chloride, salt. Okay? Now, one reason that chloride is larger percentage by weight than sodium is a chlorine atom is heavier. Chlorine are way over here in column 7 on row 3, whereas sodium is column 1 on row 3. You got a lot of more protons and neutrons to make up chlorine than you do sodium. So that's one reason. But again, others, there's more positive ions that will combine with chlorine, the chloride, than you have sodium. Sodium mostly does chloride. So chloride is a negative ion, excess of electrons. Sodium is a positive ion, deficit of electrons. And it's only one. One extra electron here, one deficit of one electron here. Sulfate is a negative ion, but it's a -2. So it's missing 2 electrons to be neutral. That's way on down the list. Magnesium, a +2, a deficit of 2 electrons. Calcium's also +2, deficit of 2 electrons. Potassium, here's one of the arrows. That should be a plus, okay? Not a minus. Sodium is a plus. And I think your table in your book has that corrected. That's on page 24-14. So let me put potassium as a plus ion, not a minus ion. That's a mighty big thick plus, okay? The next one is not nearly as serious here, but bicarbonate is also a minus, but that minus should not be down here. It should be a superscript minus, not down here with the subscript 3. So that should be up there, but it's correct. It's just in the wrong location. This should be up here. Again, in your book is printed correctly, okay? And bromine is a minus ion. Pretty low percentage too, okay? Percent by weight, 0.19, that's pretty small. And that all added together comes up to 99.89%, so we're missing 0.11%. That could be other things, and that could be all sorts of other things. Okay, so those are your ions. And this stays pretty constant, except when you have flooding and stuff like this, these could get out of balance. Okay, let me erase the ink because it's messing up. Okay, back to the nature of seawater, okay? This is what we mean if you have 1,000 grams of seawater, salt water, okay? This right here, an average of 35 of those grams. 1,000 grams is 1 kilogram, okay? 35 of those grams are your salts, and 695 grams are your pure water, Okay? So that's why this is not 35%, it's 35 per thousand. 35 grams of salt for every 1,000 grams of seawater, salt water.
Say it one more time. I kind of got it just yet.
Okay. If this was a percent, that would be 35 grams of salt for 65 grams of water for 100 grams of seawater. Oh, no, I don't even think 65 grams of water could dissolve 35 grams of salt. So this is 35 grams per kilogram, which is 1,000 grams of seawater. Okay? That means 965 grams of that is pure water. This is water with salt in it. That's how much salt it has in it. 35 per 1,000, not percent. Cent means 100. All right. Now, there is another example or two here. And it's just playing around with numbers. And again, they got their salinity right, 31 per 1,000, not per the 31%. Okay, you can look at those if you wanted to. I'll leave it up to you.
I want to take a break.
Sounds like a good idea.
Thank you so much.
What time is it, by the way? 3:30? Sounds like a good time for a break. Well, we're going to take roll at 3:45. Want to take a break and then come back and take roll? Okay. All right. I'll start then, before movement of seawater, to talk about estuary pollution. So I'm going to put this on the projector. Okay. Is it 3:45 yet, or we still got a few minutes?
It's 3:39.
3:39, okay. So that was a 9-minute, 5-minute break. Okay.
You get ready to take this?
Huh?
You get ready to take this? You get ready to take the test?
No, not yet. That'll be at 4. Yeah. Okay. On page 620, there is a blurb, closer look, on estuary pollution. Now, I don't know if any of you know what an estuary is, but basically that's a body of water that has sort of its own feel for it. It can sometimes be brackish water as opposed to salt water or fresh water. It can be water in just in a close area. One of the most famous ones perhaps is the Potomac River. Well, I'm sorry. What is the bay there? Around Baltimore, Maryland. I can't think the name of that, but it has its own kind of, I'm trying to find it. I don't think they mention it by name here. But you can have all sorts of things happening there, like pollution. That's what they're talking about here, which leads to contamination, which leads to production of bacteria, algae, all sorts of things that really disrupt the whole ecosystem. And that's what they're talking about here. Well worth a read. Okay? So, let's move on to movement of seawater. This is on your page 2415, which is the same place the estuary pollution was. Now, our seas are always in motion. They may look calm, they're not. They're always moving. The mixing time for Earth seawater, if you imagine how much water we're talking about, 70% of the surface of the Earth at an average of 2.5 miles deep, or something like, maybe not quite 2.5. That's a lot of water. It completely mixes about every 2,000 years. How in the world they came up with that is some rough estimates, I'm sure. So they think it's mixed completely about 1.5 million times over the approximate 3 billion years they think the water has been in existence like that. Now, two types of the motion, movement of seawater. One is near the surface, and these are the waves produced by disturbances. Disturbances can be caused by wind or other factors, sometimes tsunamis or other factors. The second type of motion are currents. The currents are movement of water from one place to another, generally beneath the surface. Okay? This is usually mostly a surface phenomenon. This is mostly a subsurface phenomenon. Though you can have some currents that reach the surface, but most of the time they're well underwater. Now, I meant to say this back when we were doing with groundwater. What you may not realize is almost like rivers of groundwater underneath that flow in these big aquifers, okay? Not quite the same as this, but it's certainly not the scale of this, but you still have movement of groundwater just like you have movement of seawater, okay? And both of these contribute to the mixing of the Earth's seawater. There is going to be an interesting graphic coming up that I find absolutely amazing. If they got it right, it's amazing. It's totally amazing. There is the figure 2414 on your page 2416, figure 2415 on page 2416. The surface of the ocean is rarely, if ever, still. There you see little ripples there. It doesn't look like it's moving much, but any disturbance can produce a wave, but most waves, the open ocean, are formed by local wind. That's what I said earlier. The waves are formed mostly by wind, but can be other things. So everybody got this one? Okay. So let's look at the waves first, then we'll go to the currents. Okay. Waves are the simplest structure. They're moving crests and troughs. Crests and troughs. Okay? Get your visual to see that. Here are what we call the crests, the points of the waves, the troughs are the low part of the wave. Second? 345. Okay. Let's pause a moment and mark the roll again. And we're missing quite a few. Bridget hasn't made it in today. Brianna hasn't made it in today. Jerome is still here. Aisha hasn't made it in today. Jacob is still here. Who's that? No, okay.
You so funny,
Yeah. Kaya is still here today, I think. Okay. Rakiria is still here today. Justin hasn't made it in. Okay. Sherlanda hasn't made it in. Tarsha is still here, keeping time. Okay. Eric is back, right? Yep. Saw you come in. Katie didn't. Whoa. Oh, Zach. I almost forgot Zach. Zach's still here. Katie is not made it in today. Did we lose Brandis? I think we did. Okay. And we just barely got Miss Lewis back. Okay. Did we lose Antonio? Looks like we may have. Okay. David is still here. Tiffany is still here. Kaylee hasn't made it in today. Donald is still here. And Shakaya is still here. Okay. Now, since most people are back, just wanted to follow up on something Shakaya said. She tried to get in touch with me today to see, if the field trip was on. Like I told you, once I know something, I'll put it on Blackboard, and hopefully you'll get it through an email. The old Blackboard would send those at the same time. I don't know if the new Blackboard does it or not. I hope it does.
No, we don't see your alerts because I had an alert from my teacher yesterday that she was at the Birmingham campus and I stayed up here till 2:30 and I was upset and I missed her class. So, no, we don't.
Okay, what kind of alert was that?
She was, we were supposed to be meeting up at the Birmingham campus and she texted us on Blackboard instead of emailing us, but it didn't, the message didn't come to my phone, so.
Oh, I see. Well, I'm not going to do the text because I don't have all of your numbers. I'm going to do an email on Blackboard. So watch Blackboard.
No email. Don't do Blackboard. Do email. Right.
Okay.
Email Bill.
Well, no, Blackboard does email too.
Don't do it
I'll-
through Blackboard. Do it strictly through your email.
The office not working right.
Oh, it's not?
This one girl emailed out.
Well, you see, I don't have all of you in one group on the email except on Blackboard. So
We may have-
are the announcements coming through on Ultra?
You need to try it and see.
Huh?
We
You
try
need
to
try
say
something. We need to do a test to see,
Okay. Yeah,
like test.
yeah,
To see.
okay, Right.
Like test.
okay.
Like
I'll try to do that this evening if I can, but I won't now. But back to Shakai's thing about giving me a phone call. If you think about Tuesday and Thursday, I have an 8:30 to 9:45 class, 15 minutes until I have a 10 o'clock until 11:15 class, and then 15 more minutes until I have a 11:30 to 12:45 class. Then I have 30 minutes right before this one. That's when I eat lunch too, if I can. Wasn't able today. And then I'm in here from 1:15 until 5:45. So I'm not in the office, but 15 here, 15 there, 30 here. That's all. So it adds up to barely more than an hour I'm in the office on Tuesday and Thursday. So I'm not going to hear many phone calls. Now, usually my work study student's in there, but she may have been out when you called. So can't count on that either. Okay. So back to the waves. Okay? Good deal. Thank you so much. All right. So waves are moving crests and troughs. If the crests are moving, the troughs are moving. They've got to. They go together. 3 characteristics that we use to describe your waves. The first of these are your wave height. That's the maximum distance between the bottom of the trough and the top of the crest. That's your wave height. Okay? The vertical distance between the trough and the crest. Then is the wave, and by the way, that's measured in a distance. That's a distance measurement in inches, feet, miles, not miles, but meters, some sort of trough measure like that. Your wavelength is also a distance measure, but that's a horizontal distance between 2 consecutive wave crests. Okay? That's your wavelength. How far it is between those crests. Okay? The third of these characteristics is a time measurement. This is a wave period. The time between the passage of 2 consecutive crests. So let's say you're sitting here. Remember, the waves are always moving. So if this one crosses at this time, and you wait till the next one gets here, measure the time between that one and this one passing at a given point. That's your wave period. Okay? And that is measured in time. Period is measured in time. Okay. Any questions on that? All right. Oh, still doing? Okay. Now, where this is going to come to play is you're going to be talking about wave height, wavelength, the relative sizes of these as you go deeper and deeper. Because this is all a surface phenomenon, But it affects the water just below the surface and even a little further below the surface. But the effect gets smaller and smaller and smaller until somewhere down here there's no effect at all. The water is just sitting there. Okay? So that's why we're focusing on these characteristics, because these are the things that we use to measure the effect of this activity. Okay? So, ocean waves primarily are from the wind. Okay? The characteristics depend on these three factors. Those three characteristics we saw on the last slide depend on these three factors here. The first is the wind speed. How rapidly is the wind blowing across the ocean? The more rapid the blowing the wind, the bigger the wave heights. Possibly the longer the wavelengths. And certainly could influence the period of the waves as well. So that is one, the wind speed. Okay? Second factor is the length of time that the wind blows. So if you have a wind that's changing every 15 or 20 minutes, the waves are just going to almost cancel each other out. But if you have a consistent, persistent wind that blows for hours on end, then that will also perhaps lengthen your wavelength, increase your wave height, and perhaps do something to the period of the wave as well. Okay, so that's the length of time the wind blows. The next is what you play with your nose. It's fetch. And that's the distance the wind blows across open ocean. And if you can imagine, the fetch in the Pacific can be significant. Because there's a lot of open ocean there. But you would have to have wind patterns that blow for long, long distances. So basically, you can have a lot of fetch off even small bodies like the lakes and things too. Because quite often your wind patterns are disrupted in here too, so you don't have it. But the fetch is a distance the wind blows across the open ocean. Whereas length of time, that would probably influence your period because it's a time measurement. Wind speed is a combination of distance and time. So, I've sort of given some simple illustrations, but actually the complicated mixture of wavelengths and wave heights that are generated from these various factors, it really does get to be complicated. And I can remember being in the Navy and looking. Your swells would be coming from this direction, the waves could be coming from this direction, and you have ripples that seem like they're all confused going in all sorts of directions. It can really be complicated. Okay? The smaller waves dissipate from friction within the water. Believe it or not, water has friction too. Has anyone ever water skied or seen someone water ski? Okay. How is that going to happen? Friction between the water and the ski. If there wasn't friction, it just sinks. There is friction there. Okay? Or surfboarding or other things like that. Okay? So smaller waves dissipate because water has its own friction, you say, between the molecules, trying to keep them in place. The larger waves last longer, they travel faster, and eventually coalesce into what they call a swell. Okay? So when you've had a large amount of wind speed, basically what wind speed gives you is the energy to make that, because kinetic energy is 1/2 mass times velocity squared, so that velocity, your wind speed, that contributes to the energy of the wave. And that will contribute to larger waves that also last longer, travel faster, probably because of that wind speed, and eventually coalesce into a swell. So we used to talk about this in the Navy. We would give the report, the waves are from this direction, the swells are from that direction. Sometimes they were the same. A lot of times they were slightly different. Sometimes way different, okay? Because the larger waves over longer periods of time, they produce the swells, whereas if you've had a change of wind recently, that will produce new waves, perhaps from a different direction. Okay? The swells are the larger scale. Did everybody get that? Okay. Did you? Okay. So let's look at those swells. They carry energy, but really do not transport much water. Whereas the waves, the water is actually moving. The swells are basically the energy. The same water molecule just goes up and down. It doesn't travel laterally, or not much at all. Whatever it travels this way, it travels back. It travels this way and travels back. So it's not a transport mechanism. The swells are not. The waves are. The individual particle motions are basically circular. Okay? And in these swells, and this again is where we came up with those characteristics of the wave, the diameter of the swell, of the circular motion of the waves, are equal to the wave height. Okay? Now, this is all interesting stuff, but it's not all that crucial stuff. Okay? So your swells carry the energy, but not the water. The individual particles basically go up, go down, and all the time are just basically traveling in a big circle. The diameter of that circular motion is your wave height. That's near the surface. As you go down, and you go down 1/2 of a wavelength, which is a weird reason. One wavelength would be here, 1/2 of a wavelength here. Past that, you have hardly any motion. No movement below the depth of 1/2 wavelength. It just sits there. Here, you have that circular motion going on. Down here, no motion. Okay, unless you got currents. Now, what in the world are your white caps? They happen when your swell, or when your crests get really tall and the wind blows them over. And that's what makes what they call the white caps. They form when the top of a swell is toppled by a strong wind. Okay? So you have the crest there, and when you have a strong enough wind, blows it over and makes the white caps. So you see this one illustrates why we worry about wave height. That gives you the diameter of the circular motion of the water. The wavelength tells you how deep that circular motion goes. Beneath that, you don't get any of that circular motion at all.
4.
Huh?
4 o'clock.
4 o'clock. Okay, let's see what okay. This is probably not a bad place to end. We have just done swells, but we haven't gotten to shore effects. I'm trying to find this in the text. Okay. I'm going to estimate it's somewhere around your page 2417. I'm going to guess somewhere about the first column, near the end of the first column. I'm going to erase this one. Okay. I'll put my marks there. Are there any questions before I shut down the system to start loading it up? Sorry, I'm cutting